context is torque about an axis. When you calculate the torque of a force about a point P having the coordinates x2, y2 and z2. With respect to the reference point O, it may not be the origin for all times, because at origin we have the coordinates 0, 0, 0. But in general, this point need not be at the origin. This may be the reference point. Let its coordinates be x1, y1, z1. So the position vector of the point of application of the force can be given as x2 minus x1 I cap plus y2 minus y1 j cap plus z2 minus z1 k cap. Let the force have three components: Fx, Fy and Fz. The torque of the force with respect to is given as tau is equal to R cross F. This is the R and this is F. In tabulated form, we can write in terms of determinant Ij k, I cap, j cap and k cap, x component of the R vector, y component of the R vector, z component of the R vector. The three components of the position vector we have written. Then x component of the force, its y component, its z component. This can be written as I cap, j cap, k cap. Let it be del x, is del y, is del z. Fx, Fy, Fz. We expand it to I cap into Fz into del y minus Fy into del z minus j cap del x into Fz minus Fx into del z plus k cap del x into Fy minus Fx into del y. In this way, we are getting three components. Well, so we are getting three components. This is x component, this is y component, this is z component of the torque of the force about this point. Therefore, the torque about this point O is equal to, I can call it tau x, I can call it tau y, I can call it tau z. Tau x plus tau y plus tau z. So this is the component of the torque about x-axis, this is the component of the torque about y-axis, and this is the component of the torque about z-axis. Therefore, a component of the torque tau about these three are the components: tau x, tau y and tau z are the components of the torque tau, torque about the point O, along or about x, y and z axis respectively. So the torque about an axis is a component of torque about a point. Torque about an axis may be a component of a torque about a point. Torque about this point has three components. Let us assume that this is the torque about any point. This torque has one component along the x-axis, another component along the y-axis, another component along the z-axis. When you add these three torques components, you are getting the resultant torque. So this is the torque about the point O is equal to torque about x-axis plus torque about the y-axis plus torque about z-axis. Let us take an example. You take a mango and you stand here. The position vector of the mango with respect to you is r, and gravity pulls the mango down. The question is, find the torque of gravity about O. The theory says that the torque of this force of gravity about O is given as r cross mg. This is x, this is y component. R can be written as x I cap minus y j cap cross mg can be written as minus mj j cap. This is x cap, this is y cap. You can write like this: minus mj x I cap cross j cap, and j cap cross j cap is 0. You know that I cap cross j cap is equal to k cap. J cap cross k cap is equal to I cap. K cap cross I cap is equal to j cap. Using this concept, we have I cap cross j cap. We can write k cap minus mgx k cap, and x is a constant quantity. Since x is a constant quantity for this, the torque of gravity about this point is constant both in magnitude wise, directed in which direction? Minus k cap direction, or inward direction, or clockwise direction, and its direction is constant, so also its magnitude is constant. Therefore, The gravitational torque about this point is a constant quantity. The next question is, find the component of the gravitational torque about O along x, y and z axis. Since the gravitational torque is pointing along negative z direction, tau x is 0. There is no component of the gravity along x direction. There is no component of the gravity torque along x direction. It has no component along y direction. It has no component along both x and y direction. That's very clear. And the total torque, gravitational torque about this point, orients along negative x direction, negative z direction. So total torque, the gravitational torque about this point is entirely directed in negative z direction, in x component 0, y component 0 and z component is mgx, and the direction is minus k cap along negative z direction or in. So this example tells us that sometimes the torque of a force about a point is equal to torque about a particular axis. You can say that the vector is completely aligned along a particular axis, and along other two axes its component is 0. So torque about an axis can also be equal to torque about a point in this case. Let us take another example. Find the net torque of many forces acting at a point. Suppose at this point F1 is acting, at this point F2 is acting, at this point F3 is acting, at this point Fn is acting. Let this point be P. Take the reference point O. R is the position vector of application of all forces. We need to calculate the net torque. The net torque about O is given as torque due to the force F1, that is tau 1, plus torque due to this force F2 about this point, that is tau 2, plus torque due to the force F3 about this point, plus torque due to the nth force about this point. Torque due to this force F1 about this point can be written as R1 cross F1, R cross F1, because R is the position vector of the point of application of all forces, because all forces act at a point P. Tau 2 is equal to R cross F2. Tau 3 is equal to R cross F3 and so on. Tau n equal to R cross Fn. You can take R common, put cross and bring all the forces inside the bracket in addition form. That is the vector of operation. R cross F1 plus F2 plus F3 up to Fn. And this is the net force acting on the particle or at the point. So the net torque is equal to torque of the net force when all the forces act at a point. This gives us the concept that the net torque is equal to the sum of the torques of all forces about that point, which is ultimately equal to the torque of or torque due to the net force. This idea is valid only when all the forces act at a point. When different forces will act at different points, you cannot write this equation. This expression is not valid when these forces will act at different points. When these forces will act at a particular point, then we can write this expression. Using this expression, we have to define the concept of angular momentum in this foregoing discussion.